Hello everyone, welcome back to my channel. I am Ganesh studying the first year computer science in Sri Venkateswara College of Engineering. Today's video assignment is on the subject digital design and computer organization. The topic is on introduction to logic gates and inverting the functions of logic gates in digital circuits. It is taken from the research paper of Taylor and Francis Journal. Abstract of the research paper is the advancements in digital circuits have led to the development of very complex and large assemblies of logic gates that are electronically integrated together to synthesize highly effective electronics, microprocessors, and computer systems. The complexity of these devices must be succinctly simplified to achieve simplest circuits. The functions of some logic gates in the circuits must be inverted to minimize the existence of noise and other sources of interference that can distort the performance of the circuit. Besides, most circuit designers and programmers often oversight thorough diagnosis of the Boolean expressions for designing digital circuits, which are embedded within the elements of notations and the Boolean expressions that are used for designing digital circuits, synthesizing and inverting the functions of six different logic gates during the simplification of complex digital circuits. Next, introduction. Digital logic technology and logic circuits are the underlying principles of communication between computers and other electronic devices. Digital logic gates use two discrete variables and they can be mapped with truth tables to represent electric signals. Electric signals can either have high, 1 or low, which is 0 voltage at a time. For this reason, it is convenient to represent these two discrete variables with true when the circuit is switched on and false when the circuit is switched off. Next, the designer of digital logic circuits typically adopt binary and hexadecimal notation systems to explain the operations of digital circuits. Usually, they also combine resistors, transistors with several electronic components whenever they intend to construct logic gates that can produce effective microprocessor-based systems. Unfortunately, designers inevitably face with several trade-offs on how they will suitably reduce and simplify the complexity of operations and whenever electric signals flow through the circuits. Studies point out that complexity in the design of digital circuits can distort the process of identifying, justifying, and mitigating the existence of noise and other sources of interference in the logic circuits. Most designers regularly aspire at designing the combinational logic circuits that will minimize the number of gates in the circuits such that circuits will still perform the expected tasks in effective and efficient time frame. The underlying fact here is that combinational logic involves the amalgamation of two or more logic gates and some basic devices together. Next, further, there are several ways that designers can combine logic gates together in order to perform the intended task. Studies have criticized the efficiency of some combinations of logic gates. For example, some combinations are efficient while significant numbers of them are less. Efficient digital logic gates also have particular ways they operate in different scenarios. Moreover, there are diverse ways to minimize the operating system numbers that can be used to design digital logic circuits without resulting into oversimplification or undersimplification of logic circuits. Nevertheless, studies have not recently enumerated that newest procedures and theorems are required to minimize the above issues so that designers can spell out how various users can effortlessly comprehend digital circuits. George Boole established Boolean functions and propositional logic operators and or. However, implementation of Boolean function has been generating diverse digital networks that often require optimization over the years. De Morgan proved that NOT gate is an inverse of AND gate. That is the function of the OR gate in logic circuits that can be changed to the function of NAND gate in the same circuits. Similarly, the functions of the AND gate can be changed to the function of the NOR gate. Beside the K-maps, which is known as Karnaugh maps, applied graphical approach to reduce the complexity of digital circuits to minimum number of gates. However, recent practical studies are needed to further re-examine combinational logic circuits and correlate them to the concept of truth tables. Furthermore, Goswami designed and investigated the implementation of XOR gate and XNOR gate together with arithmetic logical unit. The results suggest that there are many ways to implement XOR and XNOR logic gates. Next, challenges with the behavior of digital circuit network. Several theories and principles have been adopted to design the internal architecture of several classification models over the years. Nonetheless, two central problems regarding the behavior of digital circuit network begins to crop up. Showed that it is difficult to provide perfect explanations to the automation of the design of digital circuits. Secondly, operations of digital circuits suggest that it is difficult to achieve the minimum cost of implementation of Boolean functions during the design and implementation of super digital logic circuits. Studies affirm that theorems can further elucidate methods for simplifying small circuits by looking at their truth table and eliminate logic combinations. The study of the embedded elements of other gates is necessary because their existence may increase the intensity of noise that is introduced by erratic power source and some switches in digital circuit noise. Some next new theorems were introduced for AND, OR, and NOT gate. The development of very large assemblies of logic gates and new theorems that can support the manufacturing of highly effective integrated circuits can create business opportunities to digital designers in recent time. First, the theorem which tells about the elements of logical and logical OR and NOT can be suitably combined together to indirectly synthesize the exclusive OR gate. Theorem 2. All logic gates are embedded elements within hexadecimal notation in the associativity of logic gates. Proof of Theorem 1. Proof that the elements of the logical and logical OR and NOT gates can be suitably combined together to synthesize logic gates such as exclusive OR gate and exclusive NOR gate. Proof of Theorem 2. Proof that all gates are embedded elements of hexadecimal numbering notation. Further analysis of above combinational logic circuits. In the above table, it is specified. Next, we'll talk about K-maps. K-maps, also known as Carnot maps, are a graphical tool used in Boolean algebra to simplify logical expressions. Some basic concepts. There are cells. The K-map consists of grid of cells where each cell represents a unique combination of input variables. And groups. A group of adjacent cells containing ones can be combined to form a simplified term. The size of the group determines the exponent of the simplified term. Rules for grouping. Group must contain only ones. Group must be regular, rectangular, or square. Groups can be of any size, but larger groups are preferred. They can overlap, and the steps to create K-maps are: first, determine the number of input variables and create the K-map. Draw a grid with the appropriate number of rows and columns based on the number of input variables, and fill the map cells with ones or zeros. Identify groups and group them. Here is the example, which is group. It is a two variable K-map and single variable K-map. Next, conclusion of today's video topic is we have explored the fundamental building blocks of digital circuits. These gates perform logical operations on binary inputs to produce a binary output. Furthermore, we have delved into the concept of inverting logic gates, which involves changing their output to the opposite of its original output. By understanding the basics of logic gates and their inversions, we have led for exploring more complex digital circuits and their application. Lastly, thank you for watching this video. Please watch the full video.